Perfect. So hi, welcome. So nice to see so many of you here. And I know it's a bit late. We are tired, hungry, thirsty. But I promise you guys that the presentation is going to be quite cool, maybe fun, and easygoing. So please enjoy and do not use your phone because I'm going to get angry. So focus on this, and please try to learn something. So my name is Juan, and I'm a software engineer big data at LOVOO. And at LOVOO, I work with spammers and data every single day. And in this talk, I want to talk to you guys about that, spammers and data and how we are fighting them. So let's begin with a little bit of context. So LOVOO is a dating app and a social app, meaning that we have a lot of pretty people who are trying to engage into some sort of activities with other users. However, I got some bad news because the world is not a perfect place. And you guys know that whenever you have real users, there's going to be spammers. That's a fact. You have emails, you have spammers. You have web services, you have spammers. Spammers are everywhere. Now, the goal of these filthy and horrible spammers, at least in our goal, is to use the app to advertise other platforms and to try to scam other users. And this is how they look like. Don't focus on the numbers, I don't care about them. But I want you guys to see the ups and downs. One day, I could be winning the fight, but the next day, the spammers are going to come with a new technique, and then the numbers are going down. And then the spammer comes by, and the numbers change. So they evolve. The spammers evolve because they are constantly trying to bypass and beat our system. But I do the same, you know? I'm not going to be sitting there just like looking how the spammers are going to destroy the whole app. So I also need to get my stuff together. So it is some sort of fight. Here is a fight in which my main weapon is data. So in this talk, my purpose is to present to all of you what are the tools, the algorithm, and the architecture that we're using to fight all these spammers, and of course, to avoid the proliferation of them in the platform. This is my agenda for today. First, I'm going to talk a little bit about Antispam itself, the architecture, how does it look like. Then I'll be talking about data, machine learning, and algorithm, which is the cool part. And then at the end, some numbers. And lastly, unfortunately, I need to end this presentation. So then the recap. So Antispam. Antispam is LOVOO's solution to detect and to block spammers. And it uses a mix of machine learning and heuristics to identify the spammy profiles. And Antispam, it is not a monolithic system. It is actually made of over 15 components. It is written in Golang. I know it's quite strange considering this is a Python conference, but I'll talk about Python soon. And lastly, it is amazing. My opinion might be a little bit biased, but I'm sure it's really cool. And this is our stack. Jesus, perfect. We use Go, it's our main programming language in the system. Then we use Google Cloud. Now, I'm going to sound like a Google Cloud seller because I'll be mentioning this a lot. But the fact is that the whole platform runs in the cloud. Everything. Everything. Plus, we use a lot of the features from the cloud. Lastly, we use Kafka. And Kafka is our main engine to move things around. And the last thing is a package called Goka. And Goka is a library, an open source package for Golang that we wrote in-house to interface Kafka. So Goka of Kafka. Straightforward. But now, on the bottom row, we have Python, of course. That's why we're here. And these are the things that we use to train our system. We have scikit-learn, everybody knows it, Keras, TensorFlow, and in that tiny corner, you can see R, because we use R mostly for analyzing our data. But now, the architecture, how does it look like? Once again, Antispam is a platform made of over 15 components, and at its center, we have Kafka. And Kafka is going to be the mean of communication between all of them. And we interface Kafka using Goka, which is a Go open source library. And in Kafka, we're going to keep our live data. So we don't use any databases for this. Everything here is stored in Kafka. Why? Well, because it's fast, and most importantly, we need to do this in real time. Because if there's a spammer now, I need to get a spammer today, not tomorrow. And it makes use of many products from Google Cloud Platform. And lastly, it runs on Kubernetes engine. And this is how it looks like. So follow me here. On the left side, we can see the client, the app, the user on his phone doing do, 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 do. So every single time the user does something fun, something cool, it's going to trigger one message, one event. And this event will be sent to the backend, or this event is going to create some changes in the database, which is this one here. This is called spanner. And also this event is going to be sent to PubSub. Then after PubSub, there's some magic process, which is going to take the PubSub message and convert it into Kafka message. And in Kafka, this is where the magic happens. Kafka is made of a lot of topics. We have around 96, 95 topics in Kafka. And these are the components of Antispam. They have funny names: Sheriff, Terminator, Photographer, Rosetta, and so on. And every single of these components is going to apply one particular technique. Each one of these components is going to try to find if the user who triggered this event is a spammer or not. So these components are going to start consuming all this topic from Kafka, all of them. And they're going to do some magic calculation. And if the component believes that this user should be punished, it's going to send something called an advice to this little guy here called the meat grinder. Now, Meaty, as I like to call him, Meaty is going to take the advice and it's going to be like, okay, should this person be punished, yes or no? And it's going to go through a lot of rules. For example, it's going to check if the user is whitelisted, because, for example, my profile is whitelisted because I shouldn't be punished. And then if the answer is yes, then we're going to trigger the punishment. This punishment is going to the back end, and the person is going to get a horrible notification on his phone saying, like, you have been kicked out of the app. But what's going on here? This is our model training section. Here is where the magic happens. So all this data eventually goes to BigQuery. And in BigQuery is some sort of, let's say, it's our big data warehouse. And from here, we're going to load our data using Python. And then we're going to train our models using scikit-learn, Keras, or whatever. Lastly, after the model is being trained, it's going to be stored into cloud storage. And once the model is stored in cloud storage, each component is going to retrieve the model, and then it's going to make it run into production. And that's the story. I'm going to give more details soon about this. But now, the cool part. This is what we like. So please get your papers, your pens, and write some. So algorithm we employ. Doing Antispam, we use a mix of machine learning and heuristic to detect and to fight the spammers. Now, the data that we use is based on different things: text, counts, images, and sequential data. And some of these algorithms are created by scratch by us, or trained using Keras or scikit-learn. But no, everything starts with data, right? Perfect, yeah, of course. And this is how we get the data into Antispam. We have three main sources of data. The first one is the LOVOO backend. The user there's no battery here. You use all the batteries. Oh, geez, so I need to hold this. Okay, I don't like this. Anyway, so let me go back. So we have three main sources of data, sorry. And in the first one is going to be the back end. And here, the user is going to do something in the app, and then it's going to trigger one event, and the event goes to PubSub. Second, we have Airflow. And in Airflow, we have different jobs that are going to run every single night, and it's going to generate some aggregational data, for example. And then we have Antispam. Antispam is going to produce some of its own data. Why? Because we like to keep track of everything that Antispam does, because it helps us in the future to develop new things. But how do we do this? Well, we have a tiny guy here. It's called the barbecue. And barbecue is the only source of information that is going to take data from Antispam. Is going to store it into BigQuery. It's called barbecue because BigQuery is BQ and BBQ. I don't know, like Barbie, barbecue, stuff like that. So this is the only guy, the only component who's going to talk to the outside. But then, now that we have the data, then we're able to learn from it. And these are our boring components, the basic ones. These are the heuristic-based one. And the first one is the terminator. And the terminator is basically just a bunch of rules. If. If you come from IPX, if you are from this country, if I don't like you, then you get punished. Then we have the behavior rules. And in the rules is another set of if, but it's more based on the behavior, how the user is using the app. For example, if a user, a female, does 15 gazillion votes in 1 minute might be a bot, because the girls don't do that. And we have the community. And the community deals with the reports. If a person gets 10 reports in less than 5 seconds, come on, of course. It's pretty obvious. You're a spammer, so you will receive one punishment. But not to the cool one. Yeah, yay. Machine learning based. And let's start with a small story. Spammers and not spammers, they behave in different ways. For example, one female, she could log in, do one like, send one message, reject all the voice in the platform because that's how they work, right? But a spammer user, she will try to contact every single person in the app. So, in conclusion, they behave in uncommon ways. And for this, we got our first person here, our first friend, and it's called the sheriff. And the sheriff is the user behavior model. And this system is going to classify users between spam and no spammer based on their behavior. And the features that we use here describe the user execution ratio of events. Sounds confusing, but give me 1 second. And so far, currently, today, the model is one logic regression model, trained using scikit-learn with a data set of over 1 million and around 30 features. That's today. Several months ago, we're using a random forest, but we decided to change because changes are nice, right? And this is how the training set looks like. This is like a screenshot of it. And here we have the columns, and each column represents one event, something that the user is going to execute. Message sent, like, event 3, and so on. And on the last column, we have the label. So what is happening here is that the first user, the first row, is telling me that 33% of all the events that the user has done in the last X hours, can say the numbers because the spammers are watching me. That means that 33% of the event has been message sent. 33% of the event has been like. So the user has some kind of really normal amount of events. Everything seems to be the same. So the user might not be a spammer, spam 0. But let's talk about the third user. Here we see that the third user, 100% of all the events he or she has executed has been event 3. So the user might be a spammer. So of course, the label is 1 and the person will get punished. So now let's move on from that. And in our app, there are 2 fields in which the user can actually write any text they want. And this is the username field, of course, because people has name, and the about me. And this is where you write like, I like traveling, I like food. I mean, who doesn't? So, of course, spammers are going to use these fields because spammers like all that stuff. And this is an example of a username. Some user might be called sexmecall1234 blah 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 9. Or another spammer might write in his about me example, in his about me field, interested in hosting me sex? Yes. Send me an email to xxxhhawdwd, I forgot the last one, f@hostingmesex.com. I was actually practicing that. So, for doing this, for dealing with this text, we came up with Rosetta. And now Rosie, for me, Rosie is like an old lady, like 60 years old. So Rosie is a component made of several text-related models. And the input of this model is going to be, of course, text. And once again, here we're using Logit, training scikit-learn. And to give more detail about them, we have 2 different kind of models, the about me and the one about usernames. And regarding the about me, we have 1 model per country because we have different languages, right? So we realize that it is more work to have 1 model per country, but it works better. And the training set varies here. We have from around 40,000 Ks to 100,000 Ks observation. And the data processing step is quite straightforward. We lowercase everything, we remove the stop word, we filter some rows, and then we vectorize the text. Regarding the other one, the username is quite similar, but so far we only have 1 model. We might change this in the future. And the training set is created from around 15K here, less than before. And the data preprocessing step is similar, except that we use bigram here. And we use bigram like character level bigrams. So we are going to separate each character into grams. So it's quite similar. And let's talk about images, no more text. And just suppose that you're playing in the app, scrolling, and you see this picture of a, handsome person. And you have like this text. Again, interested in hosting me sex, and you are like, Jesus Christ, these people again? So, of course, it makes me angry. At least it makes me really angry. So for this, we came up with these 2 guys, the spotter and the photographer. And the goal of the spotting and photography is to deal with images. And the spotter is going to detect. It only detects text on the images. Remember, detection. And the photographer is going to extract the text. And this text is going to be sent to the terminator, the first guy that I mentioned before. And the terminator is going to determine if the person is good or bad based on the text, because we have a lot of rules in the terminator. And the spotter, written in Python, is actually our only big major system that is actually running in production in Python. And we use OpenCV for the detection. And the extraction part is going to be done by Google Cloud Vision API. And this is how the whole system looks like. It's a bit confusing, but let's start from the bottom left. So here we have first the user. He's doing something in the phone. He's going to upload one image. This is going to trigger one picture upload event. This event is going to Kafka. And then Kafka is going, then the spotter is going to acquire this event. And we're going to talk with cloud storage. We're going to retrieve the picture. The picture goes back. And then we check if there is text. If the answer is yes, only if the answer is yes, we're going to create one text detected event. This event is going to Kafka. And then the photographer is going to consume this event. And once again, we're going to retrieve the image from cloud storage. We're going to communicate with Cloud Vision API. And Cloud Vision API is going to tell us if there is text. If the answer is yes, go to the terminator. And if the text is bad, the person will get punished. Now, why are we doing this? Well, money. Cost. In an optimal world, we would send every single image straight to Google Cloud. But, I think the price is quite high. It's like $150 every 1,000 images. And we deal with like millions and millions of images. So at the end, it's really, really expensive. So we rather first here just only check if the person actually has text. And if the answer is yes, then we send the picture to Google. So now, the new stuff, the cool things here. And the first one is the tracer. And the tracer, with its fancy name, is the component that deals with sequences. And the tracer tries to answer the question, how is the user using the app? What is the order of events executed by the user? And its goal is going to be to detect the spammers based on their sequence of events, which we call actions. And the model is one RNN, trained with long short-term memory, LSTM units, and also trained in Keras. Now, the training is done in Google Cloud ML. Why? It's quite straightforward. We don't actually need to start machine with like a billions GPU and so on. We simply do the script, we upload the script, we click start, and then the whole training is going to be done automatically in Google. Also, the model is served in Google, so we don't have to have an extra machine just to serve the model. We're simply using the tools that Google is providing us. I know I'm talking a lot about Google, but... And this is how they look like. Please follow me here. We have three different kind of actions in the tracer. The active one. And the active are the actions that the user execute. I like a person. I send you a message. Then we have the passive one. And the passive are the events that are done upon me. You like me. You write me. And so on. Then we have the third one. And the third one is the time bucket. And here we're going to take how much time, the time difference between these events and the previous one, and we're going to bucketize this into some sort of actions. So meaning that we don't actually keep the exact time, we simply bucketize this. For example, if it is the first action, we write the number 1. If it has been from 0 to 5 seconds, we use the number 2, and so on. And this is how they look like. This is an example of one sequence. The first one means like the timing, means like number 1 means that it's my first action. The one in blue are the active one, and the one in capital letter or orange are the passive one. So this user, the first event was a like, then after 0 or 5 seconds, did a like, then once again, it got a like, but then around 20 or 1 minute after that like, the person got a dislike. And this is even cooler, right? This is how they look like. On my right, I have a non-spammer, and on the left, I have a spammer. Now, the white color is actually an image that represents the action, so it's better for us to know how they look like. The white one means the passive events, the events that are done upon me. So the non-spammer has received a nice amount of images, a nice amount of likes or messages. Then we have the green one, and the green ones are the messages. So the non-spammer person, these both cases are female, sorry. She logged in, She sends some messages. Maybe she has like 1 friend, 2 friends, 4 friends. I don't care. And then we see all that red. What are red? Can anyone guess? Dislikes. So this person decided to dislike 1 billion people here. And blue are the likes. So maybe there were some likes here across between all these dislikes. Now the spammer, this guy, Jesus Lord, he's only going to like every single person. Likes. Why? I don't know. But here we can see that the person is going to like and then messages. And it does so many events so quickly that it doesn't have time. You know, it fills the buffer of events so quickly and you barely see any white events because they add so fast. And currently, so far, we're only using 500 events. 500, like the sequence has a max of 500 because it's quite expensive to keep all this data in Kafka. We try to keep the messages in Kafka under 1 megabyte. And between all the sequences and the timestamp and this information, we have around 600 kilobytes per message. So we need to keep it slow, otherwise Kafka is going to crash, and my neck also might crash. Because if I kill Kafka, the whole company goes down. Oops. But now, our last experiment. This one is called the conviction. And the conviction is a meta model, I like to call it, that uses the scores of all the other components. It's not confusing, right? But the features are going to be the confidence value of the other components, Sheriff, Rosetta, Tracer, and so on. And we had this crazy theory, you know, the theory that you discuss when you are in the bathroom, in the hallway, in the elevator, that maybe, by using combinations of all these components, we might lead to more punishment. Because sometimes one component could be almost about to punish someone. But what about if I look at the scores of this one and this one? Then I might be able to punish you. And currently it's in dev, but it would probably be another logit, random forest, or just a bunch of heuristic produced by hand. And this is an example of the training set. Here, each row corresponds to one of our components. The first one is Racer, Cherry, Rosetta username, and so on. And in the first user, we can see that all the scores are quite low. The minimum is 0, the maximum is 1. So this person might be a normal user. But the second person, 0.60, 0.75, 0.40. So there's something a bit fishy here. So the user might be a spammer. So we're just going to punish the user and whatever. The next one is quite obvious. The person has 99% in the tracer, and our current threshold is 95. So indeed, it's going to be a spammer. And the last person is the same. It has 80%, like 0.80 in the Rosetta username. But now, the model algorithm, let's move on to something more interesting maybe. And this is the automatic training. How do we keep track of all this system? Personally, I can't do it by hand every single day because it takes a lot of time, effort, energy, and so on. So we designed a really simple and cool pipeline that is going to train and reload some of these models. Now, this is the important part here. Please keep in mind, we only apply this to the models that we fully understand and that do not represent a high risk. Why? Well, just imagine that we train one system at 2 a.m., the system gets automatically deployed in production, and when I go to the office the next morning, I realize that my system blocked the whole user base. Bad news, right? Then I have to pick up my stuff and go home. However, this is how it looks like. It's quite confusing, but please follow me. Once again, top left corner. So here we have our training script. Rosetta username, Rosetta, about me, Germany, and so on. Then we're going to get the existing data set. We keep the data set into BigQuery. We get the data set, then we're going to get the new data. Why? Because we execute this around every 2 days. So if I'm dealing with usernames, I'm going to get all the usernames that has been created in the last 48 hours. Then I'm going to create, and by the way, all this data is in BigQuery, once again. So I'm going to create my new training set, and then we're going to train. And here during training, we're going to clean the data set. This is automatically, please. It's going to clean the data set. It's going to find the best hyperparameter. It's going to do blah, blah, blah magic. When this is done, we're going to create one Kafka message. Again, everything here is Kafka. And this message is going to say like, hey, this model has been trained. This was the accuracy. Good luck with it. And then each single component is going to retrieve. It's going to consume this message. For example, Rosetta is going to consume the message. And when this happens, something cool is going to happen here. when we train, we're actually going to save the model into cloud storage. But what do I mean by saving the model? Well, in the case of logit, we know that logit is basically two things, coefficients and intercept. So we're going to store the coefficients and intercept into cloud storage. But we need a third thing here. Since I'm dealing with data, with text data, I'm dealing with a dictionary because I'm actually using count vectorizers to convert my object, my text, into numbers. So I'm going to store my dictionary, coefficients, and intercept. So then Rosetta is going to retrieve this, and it's going to read this file, and it's going to do some magic that we wrote, and it's going to convert this into a Golang logistic regression model. So that's the magic step that's going to take a model from Python and put it into Golang, because we don't run anything in Python, because Golang is quite fast. So then we have the model, and we're going to run the production model and the new one in parallel. Then it's going to happen more magic, basically some counts and something called the Jensen-Shannon divergence. And this is one statistic that is going to measure how similar two distributions are. And at the end, after some hours, we're going to check if the test model, if the new one is better than the production one, then we're going to replace it. And then after some hours, the whole loop is going to start. Now some numbers, almost at the end. This is how the spammer percentage look like, and regarding daily active user. This is data from the first quarter, the third quarter of 2016, and the first quarter of this year. I haven't updated the numbers, so sorry about that. Now, what happened here? As you can see, the percentage of spam user is below 1%, which is amazing. It is quite the same. This is a boring table, so this one is better. The average time it takes to punish someone, and this is a roller coaster of emotions. At first, it was horrible, 2.2 hours. Then it got better, 1.1. But then something happened here. I have no idea. 2.4, it went up and down and down. And currently, we are in around 0.7. So it's been changing a lot. So now, recap and conclusion. Spammers are bad. That is good. A combination of ML and heuristic help us in the fight. And I think this is really important here because I kind of believe a lot in things written by hand. That's why we have a lot of handwritten rules. And our first deep learning model came only like 3 months ago, which was the tracer. So I think that if we use both of them, it's going to be really nice. And services such as Google Cloud, ML Engine, BigQuery assist us a lot. And for the future, we would like to finish the conviction. We would like to do more image processing. For example, we don't have nudity detection, something really simple. So if someone uploads one dick pic, can I say that? Then the person is just going to be free in the app. And then lastly, we want to do something called the anti-spam detector, which here our goal is to know if a user is 100% real. So we don't touch the user, and then we avoid further false positive. And this is the sad part. Thanks a lot for your time. Say no to spam. This is the rip of Coca and this Golang Kafka thing. And yeah, now you can upload, please. Yeah, do it.
All right, thank you, guys. We have time for 2 questions. We have just one mic, so if you one could repeat the question. And there's your mic.
Hi. You're a bad guy, yeah. I'm not for Still, you're a bad guy.
Yeah. But one of the most effective methods I found is that companies use just blockers for IP ranges from data centers, from proxies.
Yeah. We have that, yeah. I mean, we have that, but that's actually the terminator. We have like a billion, gazillion IP. But, it's quite silly and anticlimactic when, there's a spam wave and then just add the IP and that's it. I want to do something more interesting. But not in every single case is that because, spammer, like the really smart ones, they change their IPs and they own like, I'm not lying, they could own like 1,000 different IPs because they also use IPv6. So, it's like the low hanging fruit. Cool. Next, yeah.
Okay. Thank you a lot. So I have a question. How do you collect the ground truth? So not to make it in a circle.
Okay. How much time do I have for this question? Jesus. How? Okay, so Jeez, man. Okay, well, it's been like a long story because when I joined the company, everything was based on rules. So you cannot start building on that, you know. For example, if you know that a user does 40,000 likes, then it's a spammer. But besides doing likes, this person comes from one place. This person has an IP. This person has this execution ratio. So you keep building on that things. There's something that sometimes we do. It sounds horrible, but I call it eating our own shit. So sometimes we cannot train using our own labels, but we have to be 100% sure that this person is actually like that. So there's not an actual answer for that, but it's been a process of building on your own things and a lot of tweaking here, a lot of tweaking there. But since we're talking about big data, then sure, you could have some false positives, some bad example, but at the end of the day, it's not really going to matter. It matters, but we have never had like any big issue. So, I mean, to summarize the question, it's been a lot of work. Yeah, I don't have like a real answer because it's been a process that we've been working for like 3 years already. And there's some manual label also.